So if we're going to find the points of inflection for the graph y equals e to the negative x squared, we need to find the second derivative. So we'll need the derivative y, but we'll be really interested in the second derivative, which is going to be y double prime. So when you take that first derivative, don't forget that we're going to have a u value here. All right, so the derivative of e to the x, say e to the u, is going to be e to the u du dx. And so with this guy, we've got that u of negative x squared. So what's our derivative going to be? It's going to be e to the negative x squared times the derivative of negative x squared. So negative 2x. That's our first derivative. So the second derivative now, though, is going to be the product rule, because we've got two separate things going on here. So the derivative of the first, we'll do that in purple. Well, it's just the same guy. The derivative of the first is going to be e to the negative x squared times negative 2x. Okay, that's the first guy, times the second, negative 2x, plus the first, e to the negative x squared, times the derivative of the second, negative 2. So we can combine all this down. Notice that in each piece we have an e to the negative x squared. So we'll just factor that part out. And what do you have left? You've got 4x squared on the inside, minus 2. Okay. So this shouldn't be horribly challenged, but that's your second derivative right there. So what we want to do is, if we're looking for a point of inflection, we need to set each piece equal to 0. So we're going to set this guy equal to 0, and then we're going to set this guy equal to 0. And when we do that, we'll find where our points of inflection occur. So if I take e to the negative x squared equals 0, and then 4x squared minus 2 equals 0. So let's go with the easier one first. This is going to be 4x squared equals 2. So x squared equals a half. So what do we get? We're going to get x equals plus or minus 1 over the square root of 2. Okay? So we're good on that guy. But what about the e part? Well, how can we get that e how can we look at this? E to the negative x squared. Well, when we are looking at that guy, one of the things that we have to consider is that e, the graph of e, is almost always positive. So unless we've moved it up or down. So if I look at e to the x, just e to the x, it's going to look like this. Well, if I look at e to the negative x, it's going to look like this. Hey, both of these are greater than 0. Both of them don't cross 0. So what ends up happening is with this guy right here, he's never equal to 0 at all. So the points that we're interested in just turn out to be these guys. All right. So what are the points of inflection? Well, we get a point of inflection when x equals 1 over the square root of 2, and when x equals negative 1 over the square root of 2. So substitute those guys back into your original equation. So let's move this derivative out of the way here. Let's get rid of the derivative rule. We don't need it right now. And we're going to have e to the negative 1 over root 2 squared. So when x is 1 over root 2, then we're going to get e to the negative 1/2 power. And when e is negative 1 over root 2 squared, we're going to get e to the negative 1/2 power. And these two guys right here, these are your points of inflection. Okay, this guy's an interesting problem we have the graph of the derivative. So we want to know, based on what we see, and this is going from -4 to 4, on what intervals does the function increase? And remember, the function increases where the derivative is positive. So if we kind of split this up a little bit into some points here, my derivative is positive from -infinity to -2. Okay, my derivative is positive from -2 to 1, and my derivative. So right here, my f prime of x is greater than 0, and then on the other side, from 1 to 4, my derivative is less than 0. Okay, these are really important things. And so, on what interval is f of x increasing? It's increasing from, well, I wrote -infinity here, but this would actually be 4. From 4 to 2, to the -2. And at -2 it quits increasing. But then it starts increasing again from -2 to 1. And so that's where my function is increasing. Okay. On what intervals is the graph concave up? So when you're looking for that, you're looking where on the places where the derivative is increasing. And so where's the derivative increasing? The derivative increases from here to here, okay? From -2 to 0. -2 to 0, we're increasing. And from this point right over here, which looks like it's 3, from 3 to 4, the derivative is increasing. And so that's where we're going to find our concave up parts. So where does that happen? It happens from -2 to 1, or I'm sorry, -2 to 0. These should actually be open intervals. So let me just... together with 3 to 4. So again, just look where your derivative is increasing. At which x-coordinates does f have local extrema? And this happens when the derivative is equal to 0, and not only where x is equal to 0, but where the sign changes from positive to negative. Okay, and there's only one place on our function here, on our derivative graph, where the derivative changes from positive to negative and crosses the x-axis. And so, which x-coordinates does f have local extrema? The only x-coordinate that will occur at is when x equals 1. Okay. The other thing that we can need to look at are the endpoints. And so our endpoints on this one are 4 and -4. So we would also say that there's an extrema at 4 and an extrema at -4. Okay, so there's all of those guys. Part D then. What x-coordinates, what are the x-coordinates of all inflection points of the graph of f? In other words, where the graph changes from concave up to concave down. And so then what we want to look for is the places where the derivative has maximums or minimums. Okay, where you have maximums or minimums, that's where you have concavity changing. And so when you look for maxes and minimums, you're looking at -2, 0, and 3. So what x values are we concerned with here? We're concerned with the x values of x equaling -2, x equals 0, and x equals 3. These are the places where you have 0 change, 0 slope. So the derivative of those will be your points of concavity, your points of inflection on your second derivative. And then lastly, it says to sketch a possible graph of f on the interval from -4 to 4. And so using the information that we've got Um, it it would be something along the lines of, and this isn't an exact thing, but if I have a graph here, and I'm going to go from -4 to 4, and we'll just call this guy -4, and we'll call this guy 4. Okay, my graph has to look not exactly like this, but something like this. Okay, where's my derivative is positive from 0 to 2. Okay, and so that means from 0 to 2, my graph is increasing. Okay, so it's got to look something like from 0 to 2, my graph is increasing, increasing, increasing. And then at 2, we've got a derivative of 0, which means that it flattens out right there. We also have concavity change. So I'm going to have this point. So this would be at -2. And then again, my derivatives increase is above 0 all the way to 1. So my graph increases all the way to 1, and at 1, my derivative is less than 0, so my graph decreases. And again, there's a change at 3. So out here at 3, I'm going to have a change in concavity. So it should look something like this. And this doesn't have to be exactly how it looks, but this is just like a rough sketch. And you just put all of these things that we just talked about together. And so we've got local extrema at 1 and at 4 and at -4. Okay, we don't have local extrema right here. We don't have a max or a min. Okay, because the sign doesn't change on the derivative. So anyway, that's a little tricky for these guys, but with some practice, you can start finding some of these patterns.